Okay, so this is the continuation of the response spectrum lecture I presented on my first video. So in this, I would like to present to you examples of response spectral graph and of also the records, acceleration records coming from actual earthquakes. Okay, so we have this first figure. An example of the maximum displacement relative to base versus the natural frequency in terms of cycles per second. Okay, so this is now a displacement response spectrum for an elastic system. When you say elastic, you are referring to the oscillator undergoing elastic behavior. Okay, so the oscillator, or simply the system itself, behaves elastically, and the observation of such displacement is confined to such elastic behavior. So hindi natin palalampasin dun sa inelastic response. Okay. So this is coming from an earthquake in California, specifically in El Centro, Southern California, 1940s. Talagang matagal na to, no? The good thing about El Centro is kumpleto yung mga record nila dun eh. Kaya napag-aralan nila yung uh, response nung mga buildings nila on that site because of their existing data obtained from the accelerograph that they installed, no, in each and every part of California, no. So specifically ito sa El Centro ito. Okay, so we also have an earthquake record of El Centro, May 18, 1940. The same, pareho rin pinagkunan sigurado nito. So this is again a graph of a spectral acceleration, normalized I think, with respect to time duration, no? So time t. Okay, so this is an actual seismograph that, or accelerograph, that was recorded by their accelerometers. The seismogram, they use the time. Ito yung record nila. Okay. So we also have here an example of tripartite response spectra. So when you say tripartite, the response is already graphed into three, okay, three responses. So displacement, velocity, and acceleration. Okay, so we have the displacement on the diagonal. So if you see, this is your displacement, okay, axis. Okay, so you see your axis here, it's the displacement, and then you also have your velocity. So this is your axis going, okay, so this is for the displacement. I think we have here starting from here, going upward to the left. Okay, so that's your displacement. For the velocity, this is here going upward, and for the acceleration, which is this one here, This axis is going from here, going right, going upward to the right there. Okay, so you have a tripartite response spectrum because it involves three responses at the same graph. Again, this is for elastic system, and the source is from El Centro 1940 earthquake. We have also a design spectrum graph, and they are commonly normalized. So kung ito actual, no? So response spectrum ito, actual values, ito tawag dito is normalized design values. Okay, so when you talk of design values, we are taking the average of the different responses brought about by comparing the analytical graph with that of the experimental graph. Okay? So, average and normalize. Normally, pag sinabing normalize, it's measured in terms of 1 unity, 1 times the gravitational acceleration. Okay? So, if you get a 0.1, you have to multiply it by the gravitational acceleration because your reference for acceleration on earthquake is your point of reference is actually the gravitational acceleration. Okay, so remember that class, design spectra takes into account the average, getting all the maximum. That's why if you will notice a smoother curve is obtained from this. Okay, when you say normalize, you are referring to the acceleration which is a peak ground acceleration of 1.0 times the gravity. Okay, so this is also an example of an elastic design spectrum normalized, but this time damping is considered. By the way, this graph here considers damping in terms of these percentages here. Okay, so this is quite confusing kasi pinagsama-sama na dito yung all the responses assuming different types of damping. Okay? So nandito ka na sa maximum of 10% um, for natural damping. Okay, but this is now a specific design spectral graph normalized to 1G for a 5% damping. Okay, so the only reason why I separated this is because the other spectral graph are actually obtained by, when I talk of the design spectral graph, are obtained by simply taking into consideration this first graph here on the ground motion maximum gravitational acceleration of 1.0 g. So if you get this, if you take a look at this acceleration axis or coordinate here, this is the 1. This is the basis for your normalized, okay? Normalized spectral graph. Now, for the damping uh, counterpart of 5%, what they do is only to get from the record the amplification factor, okay, which is the basis for the code, no, yung mga amplification factor, and this is actually seen on this table, no. So for percentage damping, it's 2.6. So ang gagawin lang nila, they simply multiply, okay, the amplification uh, 1 times 2.6. So the acceleration 2.6 g is actually uh, uh, directly multiplied on the acceleration, while of course the displacement and the velocity will have a 1.4 and 1.9 amplification factor. Okay, so for the displacement, this is now your displacement. Okay, so displacement, what axis. Okay, so this is now your displacement axis. So it's multiplied into the factor given here in the table of 1.4. So you get now the corresponding value of 50.4 inch, I think. If the original displacement is 36 inch. So you can check on that if 1.4 times the displacement of 36 inch is equivalent to 50.4. So let's multiply it. So this is 36 times 1.4. So this is 24, carry 2, 12, 14, and then 36. So this is simply 5.04. Okay, sorry, 50.4. Okay, so that's the displacement. And for your velocity, if you will look into the velocity of 48 inches per second, you simply multiply it again by 1.9. You get 48 times 1.9, you get 91.2. Okay, so you just adjust, no? You just make sure you just make an adjustment on this. Okay, so this is the velocity. So 48, and then you multiply it, and then you get the velocity there. You simply draw the graph here. Okay, you simply draw a graph here, which is 91.2. And then for the displacement, if the recorded displacement there is 36, okay, and multiplied by 1.4, you get 50. So you just get the graph there. Whatever the intersection is, you stop there. And then this 2.6 times 1 is 2.6 g. So you get that. Okay, so where do you stop now? You stop at exactly 6 CPS. No, so there's a 6 cycles per second. So at that point you stop, and then connect it to about 30 CPS. Okay, so these two values are empirical in a way na nakuha nila sa data yan, that at this particular period, 6 and 30, the graph of the spectrum curve, anyway, this just normalized and average, has a slope equivalent to this. Okay, so para siyang ito yung termination point mo sa 6, at ito rin naman yung termination point mo sa 1 velocity. Okay, so of course it can only end up to a velocity of 1 meter per second there. Sorry, we're talking of inch, 1 inch per second. And then the intersection is the actual endpoint of the graph. So this is now my plot of the design spectral curve normalized to 1G. Okay, when you say 1G, this is your basis with 5% okay damping. Okay, so that's how you do the plot of your. So if you will continue doing that, you will get actually figure 5.9 in this. Okay, basically this is your complete spectral, okay, graph. Now for other table which was derived, there is what you call from different sources like Newmark, the displacement, velocity and acceleration factors are very different. Like this is 1.4, this is 1.5, which is different from the thing that we multiplied from Newmark and Hall. Okay, so ito 1.4, 1.9, and 2.6 dito. Uh, Newmark and Riedel, iba. Okay, so iba-iba yung nakukuha nila, no? So, they computed the standard deviation and they found out that the standard deviation is quite big. Okay? Which simply means that the design response spectrum graph only approximates, no? It's actually a predictive way of assuring yourself that your design forces brought about by a particular earthquake that might hit the place is more or less gives you a safe, okay, a safe value, a conservative value based on the actual, okay, forces that will be absorbed by the building. Okay, so yun yung problema natin sa response spectrum analysis class. Although marami pa rin na mga naniniwala doon sa RSA, so yun pa rin ang ginagamit na marami. Okay, although this is only one procedure for analyzing and designing your building against dynamic forces. Okay, so on the next video, I will be discussing to you the illustrative example. So for the meantime, let's uh, stop at this point where we have to understand, okay, so the significance of RSA, or the response spectrum analysis, using the design spectral graph. Thank you.